In this video, we will talk about potential energy of reactants and products, the rates of reactions, and the role that catalysts have to do in rates of reactions. First, let's talk about things that influence the rate of a reaction. Of course, as you know from previous experience, that the temperature of a chemical system affects the chemical reaction. Higher temperature will result in an increased rate of reaction. If there are gases present, the pressure of a gas will also influence the rate of a reaction. The higher the pressure, the faster the reaction will go. If the reactants are liquids or a solid, grinding it up or increasing the surface area will also increase the rate of reaction. The reactants present themselves also influence the rate of reaction. Some reactants just happen to react more readily than others. And the last factor that influences the rate of reaction is the presence of a catalyst. The catalyst increases the rate of reaction by lowering the activation energy required, as we'll see later on. Chemical reactions are governed by the collision reaction theory. As with any other theory, it is used to describe, explain, and predict how things happen in science. In the collision reaction theory, it's used to predict and explain the characteristic of chemical reactions. Now, some of the main points of collision reaction theory is that a chemical reaction consists of entities. Now, these entities are atoms, or ions, and molecules, and these are both in terms of reactants and products. All of these chemical entities are in constant random motion. The higher temperature, the faster these molecules or these entities will move. A chemical reaction involves a collision of two or more entities. And there's two types of collisions. We could have an effective collision or an ineffective collision. An effective collision requires sufficient energy as well as a correct orientation, a correct direction of collision, you can say. If a reaction is not effective, it's considered ineffective, and in this case, the entities just merely rebound elastically from the collision. Elastic collision means that no energy or momentum is lost. Here we can visualize what an effective collision looks like. Here we have carbon monoxide reacting with nitrogen dioxide. In an effective collision, the carbon of the carbon monoxide collides with one of the oxygen, and in the activated complex, those atoms touch, the carbon and the oxygen atoms touch, and now they result in the product of a carbon dioxide and a nitrogen monoxide. So these molecules have correct energy as well as an orientation to produce an effective collision. In an ineffective collision, the carbon and the oxygen atoms do not collide. Here in this case, the only contact is made between the carbon atom and the nitrogen atom. The carbon does not come into contact with any one of the oxygen atoms. Therefore, the carbon monoxide and the nitrogen dioxide rebound elastically and no reactions occur. These molecules have collided in the wrong orientation. They do not rearrange the atoms and no new substances are formed. As we mentioned earlier, some chemicals react faster than others, even though the other variables are held constant, and some reactions require an initial input energy. Why is that? Well, to fully explain that, we have to talk about the concept of activation energy and activated complexes. Activation energy, or EA, is the energy barrier that has to be overcome for a chemical reaction to occur. Here in this diagram, we have A, which is our reactant. It has to gain certain amount of potential energy to reach the activated complex state. The amount of energy required to do so is called the activation energy. All the reactants must have this much activation energy before the reaction can occur. The input energy is usually in the form of heat, or collision or movement of atoms, light, or electricity. In this potential energy diagram, even though the net enthalpy change is negative, that is, it is an exothermic reaction, it has to gain positive potential activation energy to reach the activated complex. An example would be gasoline burning. Overall, it is an exothermic reaction. However, there must be a little bit of energy provided, perhaps from a match or a spark plug, to overcome the activation energy barrier for the reaction to proceed. Here on this slide, we have the potential energy diagram of a reaction. The energy pathway is the relative potential energy of the chemical system. So in this case, the energy pathway goes from here, the reactants, up an energy hill, and then down towards the products. In the middle here, we have the activated complex. The activated complex is the entity that contains all of the reactants, but in a collided format. So in a picture here, we can see that we have two molecules of the reactants coming into close proximity, and in the middle, we form an activated state. After the activated state is reached, the activated complex breaks down to form the products. In this potential energy diagram, we see that the potential energy of the activated state is much higher than either of both reactants and as the products. This is because as the reactant molecules get closer together, they are starting to get affected by repulsive forces and slow down. As they slow down, this means that their kinetic energy decreases. However, this decrease of kinetic energy is linked to an increase in potential energy. If they have enough energy to reach the activated state may go on to progress into the products. Once the activated complex has formed, you have now the maximum potential energy. Repulsive forces now push the product molecules apart, again converting the potential energy into kinetic energy. It is equally likely that the activated complex can go back into the reactants. No reaction would occur at this point. However, the activated complex has been reached. Let's look at an example. We have the reaction of carbon monoxide reacting with nitrogen dioxide to yield carbon dioxide and nitrogen monoxide. And we are asked to draw the energy diagram with proper axis and labeling the transition state and the activated complex. And we're also told that the activation energy of the forward reaction is 134 kilojoules, and the overall enthalpy of the reaction is negative 226 kilojoules. And we're asked to calculate the activation energy of the reverse reaction. Here is our energy diagram. We're told that the activation energy of the forward reaction is 134 kilojoules, and the overall enthalpy of the reaction is negative 226 kilojoules. So, therefore, to figure out the activation energy of the reverse reaction, we merely have to add these two numbers together, 134 kilojoules with 226. If you were to draw it on a diagram, this becomes very clear. First, you have to overcome the enthalpy loss by the products. And then you have to take into account the activation energy. So the energy of the activation energy of the reverse reaction is 226 plus 134, which is 360 kilojoules. This slide reminds us that for exothermic reaction, the potential energy of the products is less than that of the reactants. So here, the product is lower than the reactants on our potential energy diagram, and the enthalpy of the reaction is less than 0. Energy is given off to the surroundings. And for endothermic reaction, the potential energy of the products is greater than the energy of the reactants. So the products are higher than the reactants, and here in this case, the enthalpy change is greater than 0. The next thing we'll discuss is the bond energy. Bond energy is the energy required to break a chemical bond, or the energy released when a chemical bond is formed. And the overall enthalpy of the reaction represents the net of these two energies. The enthalpy of reaction is the energy released from bond making minus the energy required for bond breaking. For endothermic reactions, where the enthalpy change is greater than 0, the energy released from bond making will be greater than the energy required from bond breaking. The opposite for exothermic reactions, where the enthalpy change is less than 0, the energy released from bond making will be less than the energy required for bond breaking. The last thing we'll talk about are catalysts. Catalysts increase the rate of a chemical reaction without being used or consumed by the overall process. The catalyst is either reformed and when the product is formed, or it is not changed at all. Catalysts are believed to accelerate the reaction by giving an alternate energy pathway for an alternate activation complex to form. In biological systems such as plants and animals, these catalysts are called enzymes. In a catalyzed reaction, a different activated complex is formed. This activated complex usually has a lower activation energy. And because of the lower activation energy, more molecules have enough potential energy to reach this peak. Therefore, the reaction rate will increase. However, because the products and the reactants remain unchanged, the overall enthalpy of the reaction is unaffected. Only the activation energy is lower, but the enthalpy change is not affected. One application of a catalyst is a catalytic converter on automobiles. When hot exhaust gas exits the engines, it is passed through the catalytic converter before being exhausted to the environment. In this catalytic converter, we have a massive network of a honeycomb ceramic. This honeycomb, first of all, increases the surface area of the reaction to increase the overall reaction rate. And as well, this honeycomb is coated with a metal catalyst that lowers the activation energy of the reaction that converts unburned fuels and oxygen gas into carbon dioxide and water. This catalytic formation provides a lower activation energy for the reaction to happen at a lower temperature, and this catalyst is usually a mixture of platinum and other transition metals. This catalytic converter reacts very rapidly because of the catalyst as well as the increased surface area. And this converter converts unburned fuels, also known as hydrocarbons, carbon monoxide, and nitrogen oxide compounds into less harmful emissions for the environment.